Morning, everyone. Thank you so much for joining us today. I hope everyone is doing well and staying safe, especially our colleagues along the Gulf Coast and in Houston preparing for the impact of Hurricane Laura later today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled Using Composite Pipe to Overcome Deepwater Riser Design Challenges. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Rohit Shankaran. Rohit is a principal engineer for 2H in Houston and has over 12 years of experience in design and analysis of riser, jumpers, and conductor systems and integrity management of subsea equipment. He has specialist experience with steel catenary risers, flexible risers, drilling and completion risers, and rigid jumpers. He has a master's degree in mechanical engineering from Texas A&M University, and he's also a registered chartered engineer with the Institution of Mechanical Engineers. He has been with 2H Offshore since 2010. So with that, I'm going to pass things over to Rohit to get us started.
Thank you for the warm introduction, Victoria. I'm excited to be here today speaking on this topic and hope you all find this information helpful. Today I'll be talking about the challenges facing deepwater risers and the potential application of composite pipe to overcome these challenges. I'll start off by highlighting the design challenges for deepwater risers, give an introduction to composite pipe, discuss the benefits and limitations of composite pipe in the context of riser design, highlight some of the key aspects of composite riser design, followed by a case study where we compare the composite riser response to some of the other riser types out there, and close out with final remarks. I'll start off by highlighting some of the key challenges for deepwater riser design. As hydrocarbons are discovered in deeper water depths and projects are sanctioned and installed in deeper water depths, one of the main challenges for riser design has been managing the increased hang-off loads, and this impacts both the riser and vessel selection. In deep water, the increased top tension results from for requirement for thicker wall pipe, particularly if the pressures are high. Buoyancy may also be needed on the risers. This results in design challenges, such as increased material and installation costs, and it also limits the riser options that are available and that can be used. Some of the secondary challenges also need to be dealt with, such as high pressure and temperature, high CO2 and H2S, particularly in the Brazil environment, and then harsh environments, which are typical of both Brazil and Gulf of Mexico, where a lot of these deep water fields are installed. Application for flexibles in deep water is limited, and the track record is limited as well. And this is highlighted by some of the failures of deep water flexibles in Brazil in recent years. And therefore, rigid risers are really the primary solution. Hybrid risers are a good option as well, but in the current market, they are expensive to design, fabricate, and install. So perhaps not the best alternative at this time. As a result, options are needed. In a sense, riser technologies needs to keep up with the demand that's out there. So the real question is, why not just go with rigid pipe? Well, the main reason here is weight. As we go deeper, you may need larger wall thickness to account for the increased depth, and if pressures are high, that makes it worse. And as the weight increases, with that, the material and installation costs go up, and it also limits options for the host vessel and also pipe size as a result. Even with lazy wave risers, the weights can be quite high, and especially if you want to use them with something like a turret mode FPSO, the options do get quite limited. And then that also impacts hang-off structure design as the hang-off loads go up, which means you may need longer taper joints or stress joints or bigger flex joints, which again increases cost and installation it poses installation challenges. And if you have sour service, then you potentially need cladding on the line, which again makes it more expensive and heavy. Um, and that also impacts the schedule. If installation, if the design gets bulkier, then installation takes longer. For example, here you could see how the installation of a rigid pipe from start to when the installation starts is about 3 times longer than if you had something that's something like a flexible or a composite pipe. So, giving an introduction to carbon fiber, this leads us to consider some alternate materials where this is where carbon-based composites come in. Carbon fibers are fibers that are a few micrometers in diameter and composed mostly of carbon atoms. It dates back to 1879 when Thomas Edison baked cotton threads at high temperatures to come up with these fibers. And the fibers that we use today, that are the carbon fibers that are used today, they were created by created at Union Carbide in 1958, I believe, or 68. Basically, they're made up of crystals of carbon fiber, and the crystals are aligned parallel to the long axis, which results in very high strength to volume ratio. And they're characterized by a unique combination of low weight, high strength, and stiffness. And the usage in recent years has grown roughly 10% year over year, and is now widely used in the automobile, aerospace, and renewable industries in many forms. For example, the Boeing 787 Dreamliner that's seen there, that's a significant part of the structure is made from carbon fiber, and almost, I think, 50% of the structural weight comes from composite materials. The adoption of carbon fiber technology in the subsea oil and gas market has been slow, but has grown in the recent years. The primary form in which carbon fiber is used in the oil and gas market, in the subsea market, is in reinforced form, where it's used to reinforce polymer materials to create composite pipe, which is what we'll be going on to next. So what is composite pipe? Essentially, as the name suggests, it's a heterogeneous combination of two or more constituents, which are intended to be better than some of their parts. They broadly can be classified into particle reinforced and fiber reinforced composites. We'll focus here more on the fiber reinforced composites in this presentation, as that is the technology that's used to build the pipe. There are two main forms in which they're used to build the pipe. One is a bonded structure, where the primary layer is made up of carbon fiber combined with some type of polymer like PEEK or PA12 or PVDF, depending on the application you want and depending on the manufacturer. You can see the two options here, one made by Magma Global, which is made of carbon fiber and PEEK, and the other made by Airborne Oil and Gas, who have multiple options. For the polymer they combine with carbon fiber, they have PVDF, PA12, and then there is the other option, which is to go with an unbonded flexible pipe. And this is where a traditional flexible pipe is modified, where some of the layers within some of the metallic layers are replaced with composite layers. Some of the options here are to either replace just the carcass with a composite, just the pressure armor layer with a composite material, or to replace both the pressure armor layer and the carcass with the composite layer, which I'll come on to in just a minute. The focus of the presentation is primarily going to be on the bonded composite pipe. A colleague of mine covered in part one of this series, covered a bit more on the hybrid flexibles. So if you're interested, I recommend you go back and take a look at that one. Looking at Airborne, so Airborne's composite pipe is fully bonded solid wall pipe with glass or carbon fiber reinforcements, with the carbon fiber reinforcements primarily being considered for riser application, whereas some of the other materials such as glass HDPE have application to jumpers or flow lines. So it's made up of an inner liner that's made of a polymer, and then the thermoplastic composite reinforcement layer, the laminate, which is the primary carbon composite layer, and then the coating on top of that, which is a protective outer coating, which also adds some weight to it. And then there's an optional weight coating that can be added to improve stability. All the layers, including the outer coating, are melt fused together, ensuring a strong bond between the layers. They can be re-terminated offshore even after pull-in, which is a big plus for installation. It's suitable for up to 250. Sorry. It's suitable for up to 250 degrees Fahrenheit, 120 C, and Airborne can manufacture this pipe based on the public domain information for up to 7.5-inch ID for riser application. Magma's pipe is somewhat different. It's a simpler design with a single wall design, and there's an option for adding an insulation layer on top. But essentially, the pipe that they push in the market is made of PEEK, which is a high performance thermoplastic polymer, and carbon fiber. And then there are two options here: the biaxial high flexible type, and then there's a triaxial type, which is focused more on high tension. The biaxial is what is typically recommended for jumpers, whereas the triaxial design, which has high tension, is typically what we would consider for riser application. So it's a continuous material pipe and can be shaped into a bend stiffener at the ends as well. According to Magma, they can manufacture this up to a continuous length of 6,000 meters, which is quite good, I think, which is probably more than how much you need for deepwater application. It has good tolerance for compression and clashing, and it can be manufactured for up to 6-inch, 15 KSI pipe, based on the information in the public domain. Moving on to hybrid flexibles. So hybrid flexibles are where the metallic layers, as I said earlier, are replaced with a composite bonded liner. So there are two types here, as you can see. One where just the carcass is just where the pressure armor is replaced and the carcass is still there. And the other one is where both the carcass and the pressure armor layers are replaced with composite. So this results in a significant weight reduction for up to 60%. And then it also protects the tensile layers from corrosion. It's better for corrosion resistance for the tensile layers. One of the challenges, particularly in Brazil, has been the high CO2. And the expectation is that the composite layer will protect the tensile armor wires from any permeation of the CO2 into the metallic layers, and thereby providing better corrosion resistance. And the weight benefit is also a significant one, which also aids with installation. The main advantage here would be that you could potentially install this with a smaller spec vessel, which would hopefully reduce the installation cost and time. Moving on to the benefits and limitations for riser application. So the main benefit here is the lightweight, which is what always comes up. This can also be a challenge, but we'll come to that in a minute. But certainly an advantage for deepwater application. They're flexible and therefore spoolable. They use the same installation methods as flexibles. They have high strength, good pressure and temperature resistance, good chemical resistance, which results in good corrosion resistance, and high fatigue resistance, which is a key one. It's also a smoothbore design, which means that a smaller pressure drop, which results in a smaller pressure drop, which is compared to a typical flexible riser, which is a big benefit for flow rates, improved flow rates. Can also be, which also means you could get away with a smaller pipe size. And they can also be configured into many shapes, which will again come to in a minute. And the expectation is that they're low maintenance, so you install them, and hopefully they don't need a lot of maintenance, which reduces your ownership costs over time. So what are the limitations? They have a limited track record for dynamic application, which is probably the main one. Bit of like fear of the unknown, if you will. Right now, they're only being used for jumper and flowline application. However, the qualification for riser application is ongoing currently as we speak, particularly in deepwater application in offshore Brazil. Material costs are also expected to be high. Carbon fiber is not cheap, especially compared to steel. But the expectation is that the cost of ownership over the long term would be less, assuming that you, yeah, you maybe don't need to spend so much on integrity management and that kind of thing. The pipe size is limited. Currently, they're limited to in the range of 6 to 8 inch, which is kind of on the lower end of what operators typically look at for deep water fields, particularly if you're using it for a production riser kind of application. 6 to 8 inch might be good enough for so some of the other applications. I think in Brazil it probably is pretty good because that's kind of the pipe size that's typically considered. But for Gulf of Mexico, I think might need slightly bigger pipe sizes, which hopefully will come in the future. They're lightweight, which is a great benefit to have, but also creates some problems due to lack of stability, particularly in the high curvature areas. And it's also not so good from an interference perspective, as it results in large lateral deflections, which are again touch on later in the presentation. Tensile capacity can also be a limitation, particularly in deep water. Something needs to be addressed. So what are the key aspects of composite riser design? Well, the first thing to look at is the configuration. In terms of the configuration options, the configuration for composite riser is really a function of water depth and the environmental conditions such as pressure and like metocean data, pressure, temperature, that kind of thing. The type of platform that's being used, the hang-off position on the platform. So I guess that's typical of most risers. So I think one thing that's good about that is the lightweight. So this gives us a lot more options in terms of the configuration. So you can not only consider the simple ones such as a catenary and the lazy wave, which are a bit more traditional, that are used for flexibles and rigid risers, but also some more complex shapes can be considered because the low weight, you can add buoyancy modules or weight coatings or clump weights to change the shape to whatever you want or whatever works really. You can also consider some more innovative shapes, such as a freestanding hybrid riser, where the composite pipe replaces the rigid vertical pipe, and perhaps even the jumper at the top, which I think the main advantage of that freestanding option is that it significantly reduces the loads on the buoyancy tank. Particularly in deep water, if you use rigid risers, the buoyancy tank design can get quite bloated and it result in a quite big buoyancy tank. But I think the expectation is that if you replace that rigid section with a composite pipe, you can significantly reduce the size of that buoyancy tank. The focus of this presentation, I'll focus on the simple configurations, the catenary and the lazy wave, because that gives us a good comparison with some of the other riser types we can consider. In terms of the design challenges, there are basically two categories here. One is the high stiffness. The high stiffness, the stiffness of a composite pipe is somewhere in the range, somewhere between what we expect for flexibles and rigid risers, and this results in high MBR limits compared to flexibles. This also means that traditional hang-off design options may not quite work, and more on this in the next slide. The second one is weight, and as I discussed earlier, the low weight results in reduced inertia, which results in increased lateral deflections. As a result, we may need to add weight coating in some of the critical sections to put back some of that weight and reduce the lateral deflections. But again, there comes with a trade-off where the weight goes up if the weight goes up. So we need to really find a balance between tension, compression capacity, and MBR. The other thing is you may need there's always an option of using more than one section in the riser, and that is also something to be considered for composite risers. And the sections can be designed such that you have an upper riser section that's designed more to more for the increased top tension for higher tensile capacity, whereas the section at the bottom can be designed more for curvature to withstand the perhaps the compression and the high curvature at the touchdown region, or maybe if you have buoyancy, then at the start of the buoyancy section. Buoyancy may also be needed for deep water application, to manage top tension as the primary reason, but also to decouple the vessel motions as I touched on, which is typically how where the typically why buoyancy is used on most riser types. So let's look at the hang-off structure options. The objective here for hang-off structure design would be to match the, as I said, the stiffness of the composite pipe is somewhere between a flexible and a rigid pipe. So the objective here would be to match the stiffness of the hang-off structure to that of the pipe. So we need something that's relatively stiff, but also flexible at the same time, as how a composite pipe is. So polyurethane bend stiffness, they have a low stiffness relative to composite pipe, particularly if you're looking at deep water application where the pipe can be quite stiff to withstand the high tensions and perhaps pressure perhaps. So it's unlikely to be suitable for such cases, but I think probably a good option for maybe some of the smaller sizes for composite pipe and perhaps in slightly shallower water depth. I think the main solution here would be, or the primary solution here would be to go with a thermoplastic based bend stiffener. So both manufacturers, Magma and Airborne, have suggested that they can form the pipe itself into a bend stiffener at the end, and that could be a potential solution. The other option could be a standalone bend stiffener that can be attached on top of the pipe at the end. However, there's limited track record for this, and many of these are still in design. They haven't been put into the water. So yeah, so some of the other options that can be considered, particularly one that is potentially suitable is the titanium taper joint, stress joint, which has high elasticity and low weight, which makes it suitable for TCP. Flex joints can also be a suitable solution. Yeah, I think more work needs to go into this in the future to look at the suitability of flex joints for use with composite pipe. Steel taper joints, on the other hand, are unlikely to be suitable due to their high stiffness relative to the composite pipe. So moving on to the case study. So presented here is a case study for composite riser in 3,000 meter water depth for Gulf of Mexico environments, and response of the TCP is compared to some of the other riser types in catenary and lazy wave configurations. Hang-off loads and lateral deflections are compared. We're looking at an 8-inch ID pipe here, and similarly, some of the other riser types that we've considered are also the same size to match that, to give us a apples to apples comparison, if you will. So just looking at the composite riser configuration here before we move on. So you can see how that's configured here. We have we have two sections here, one at the top and bottom, one designed for the high tension, one for the high curvature at the bottom. And for as you can see, the sections in green there are sections where weight coating has been added to reinforce or increase the inertia in that area to reduce curvature and improve response. And then we have a buoyancy section there that's highlighted in yellow for the lazy wave configuration. As you can see, the catenary configuration results in quite large hang-off angles needed, whereas the lazy wave can get away with a much shallower hang-off angle. Looking at some of the other riser options here, the steel riser, again, we have a hang-off angle of 9 degrees for the catenary and 8 degrees for the lazy wave. For the flexibles, we can have a much smaller angle, 4 degrees for the catenary. I think the lazy wave should also be around 4 degrees there. And the hybrid flexible, which has hang-off angle of 4 and 5 degrees for the catenary and the lazy wave. Just moving on to how the response compares between these four options. First, looking at the static tension itself without any environmental loads, you can see that the composite pipe is 50 to 75% lighter than steel and flexibles, which is quite significant. The difference is larger for the catenary configuration, even though the composite pipe has a much higher hang-off angle. It has a much lower weight for the catenary compared to the other options, just because of the static weight, the unit weight being so different in water. These differences are less pronounced when you look at dynamics, mainly as a result of there being higher dynamic amplification in the composite pipe as a result of the higher deflections, which results in a bigger tension range along the whole riser, particularly at the hang-off, where you can see here that the uh, so that composite riser about 50% lighter than steel and flexible for the lazy wave, and about 75% lighter for the catenary. And the and if when compared to hybrid flexibles, they are quite on par for the lazy wave. For the catenary, the hybrid flexibles are about 50%, are maybe about 50% heavier than the composite. As I said, the dynamic amplification factor for the composite is higher than some of the other options, but not by that much. Especially compared to steel, it has a much bigger dynamic amplification in terms of hang-off tensions. Looking at bending loads, yeah, the difference becomes a bit more pronounced and kind of highlights some of the earlier discussion on hang-off design options. As you can see, the bending loads for the TCP are an order of magnitude higher than flexibles and a factor of three, and a factor, actually, and a factor of three lower than rigid pipe. As you can see there, this kind of highlights why bend stiffeners are typically used in flexibles, but may not quite work on the composite pipe. As you can see, the hang-off loads, the bending moment particularly is higher, um, and especially for steel again, if you're considering titanium joints or steel joints, they're dealing with much higher bending moments. Whereas for composite pipe, those bending moments are much lower. So yeah, we just need to think of some other alternate options for the hang-off configuration design, as discussed earlier. In terms of riser deflections, this is where the composite pipe starts to have some issues that need to be addressed. The deflections here are 40% higher for the steel and flexible risers for the lazy wave. Compared to the lazy wave, the relative deflections are 40% higher, and it's a factor of three higher for the catenary configuration. We can reduce these deflections by adding weight and optimizing the buoyancy in the riser, but there are always trade-offs. You can only do that to some extent because there's always trade-offs in terms of strength response. So I guess the strength response first needs to be addressed. But this is something to keep in mind during any configuration design, is to also check for lateral deflections, as that could be an issue, especially if these are being added to existing systems, as it might come up. If these are being added to some existing systems where low risers with low weight are needed, you need to address any issues with lateral deflections or interference. So the final remarks here, carbon and composite materials are a material of the future, and they've gained widespread acceptance in many industries. The best suited for conditions where options are limited and a step change in technology is needed, such as in deep water, harsh environments, high pressure and high CO2 environments, or on existing platforms where additional risers need to be added and where load capacity is needed. For example, if there's a turret and you want to add a riser to a turret, but you're worried about the capacity of the turret, particularly in deep water, a composite riser might be a good option in that case. The oil and gas industry has been slow to adopt the technology, but acceptance has been growing in recent years, and some of the major operators are participating in the development of the technology. Qualification is currently ongoing and needs to be completed in order to gain sufficient confidence for dynamic application. The main benefits are low weight, corrosion, and fatigue resistance. Really, what is desirable in deep water, particularly in sort of harsh environments and highly corrosive environments. A lack of track record and high cost are the current limitations. But I think these should get better over time as they go into service. And there are also learnings that can come out of the current applications where they're being used for jumpers and for flow lines. So yeah, their track record should come through in the coming years, as they've been in the water for a longer amount of time. They also have good potential for future for the future, that they can be good alternatives for flexible and rigid pipe in any environment, hopefully in the future. Yeah, that's it from me today. Thanks again for joining. And I'm happy to take any questions.
Thank you so much, Rohit. We've actually had quite a lot of questions, so I'll get started asking those. The first question is, could you discuss the limitations of transitions to end fittings?
I think based on what the manufacturer is saying, it's, I mean, yeah, you could have an end fitting that can even be transitioned into a flange. So in that sense, they can be connected to any external structures, such as a hang-off structure or even another section of the pipe quite easily. So yeah, the expectation is that you could just have a flange connection at the end and have the connection there. In fact, I think in terms of if you compare to flexibles, they are supposed to be easier to terminate into an end fitting and can even be done offshore because it's a simpler design. It's a bonded design, so it doesn't have too many any moving parts. So in that sense, it should be easier compared to maybe flexibles or umbilicals even.
Okay, perfect. Next question is, can you have a combination of rigid and TCP in a riser configuration?
Yeah, I'm sure you can, but I think you need to be mindful of the stiffness mismatch there between the rigid pipe and the TCP. So I think the transition would have to be in a region where there's not a lot of curvature or loading. So it's unlikely that you would have it at the hang off the transition. So maybe somewhere in the middle of the water column where you don't see a lot of loads. Yeah.
Okay. What is the VIV or FIV impact on flexible risers?
Um, this hasn't been looked at in a great level of detail, but the stiffness is high, so you would expect to have more VIV effects. We've certainly looked at the impact of VIV drag amplification, and it's certainly more than what you would expect for maybe flexibles. And because of the high stiffness, we also expect that VIV, I mean, although the pipe itself is fatigue resistant, there might be other issues related to any ancillaries that are connected to the pipe that can potentially, any VIV issues on the pipe can get translated into issues for some of the other components that it's connected to. Yeah, I think VIV is certainly something that needs to be looked at in a greater level of detail, particularly if the stiffness of the pipe is high. And if they're being used in environments where currents are high, such as in Brazil, yeah, this is something that definitely needs to be addressed.
Okay. Next question is, what is the status of composite riser development and the actual application?
The current status is that many of the operators are quite interested in it. They participate. Some of the major operators are participating in the development of the technology, and qualification is currently ongoing. So the expectation is that in a few years' time they'll be ready to put into service. If I had to take a guess, maybe the next 5 years we might see one in the water, but it really depends on the confidence level and how those qualifications go and the confidence level of the operators to take on a new technology.
Okay, and the next question is, what do we know about failure modes of these composite pipes, and how do we establish an IM plan for such new technology?
The failure modes are pretty similar to what you'd expect for rigid pipe. So internal pressure, external pressure, so burst and collapse there. Mechanisms are different due to delamination and debonding, fiber breakage, geometric transition deviations such as ovality. So yeah, so those are the primary failure modes that we need to worry about. I think one of the limitations is that we're still trying to figure out how they're going to be inspected, especially if you want to look at any degradation in the polymer layers or I mean, there is some existing technology to check for the polymer layers, but the composite layer itself, I think, yeah, I think there needs to be some new techniques to check for the performance of those layers as part of an IM plan.
Okay, next question is, what softwares will be used for designing the flexible risers?
I mean, for global riser design, we still use the typical sort of software used for other risers, such as Orcoflex, or Flexcom, or DeepFlex. For the more for the more detailed design for the layers itself, we haven't got involved in that, so I don't really have an answer for that question. I think I'm sure companies like the manufacturers have their own proprietary tools to look at the structural integrity within the layers themselves.
Okay, the next question is, how do you address the low weight of the TCPs?
The low weight is really one of the main challenges. As I discussed in the presentation, one of the ways to address it is through use of weight coatings. You may need sections of varying weight coating along the length. And as I understand, that is possible to be done in a continuous section, as a continuous section. So the weight coating would be the main increased weight, or even weights added on top of the pipe would be the way to address the low weight. But I think we can't go too far from it, otherwise you're losing the benefit of having a pipe that's light. So I think this can be done on an as-needed basis in regions where you do need that extra rigidity, either for improved strength response or for reduced lateral deflections.
Okay, next question is, have composite offshore oil and gas pipes been tested for fatigue?
I'm not. I don't have an answer to that question. I'm sure they're being tested by the supplier, but I don't. I might have to get back to you on that. If you can drop us an email in the information.
Okay, perfect.
We'll get back to you.
Yeah, we can sort that out. Okay, moving on to the next one. Does the standard cover design and testing, or is it just the qualification?
The standard does cover, the F119 standard by DNV is quite comprehensive. It covers a range of issues, from a range of topics, from material selection to how to analyze response, to even testing and installation as well. So that's the design code that's out there right now, that's currently being used, is quite comprehensive.
Okay. Next question: what are the primary failure modes for composite pipe?
I think this question has come up earlier. So I think so the main failure modes are delamination, debonding of the layers, and breakage of the fiber itself. And ovality can also cause or exacerbate some of these problems, where you don't have a uniform properties in all directions if there's ovality in the pipe. So burst and collapse are really the primary failure modes.
Okay, next question. In the case study, the return is based on 100 years. Is the pipe expected to be durable for this long?
The 100 years is meant to be a return period of the environment, not to be in the water for 100 years. The service life that would be targeted for this is typical of any riser, so somewhere in the range of 20 to 30 years. Sorry if I wasn't clear in my slide there, but the 100-year refers to the return period of the environment that's considered for the strength response.
Okay, next question. You mentioned a 6,000 meter length for magma. What is the equivalent for airborne?
I'm not sure of the answer to that, but it certainly can go from hangoff to past the touchdown point in 3,000 meter water depth. So it's definitely somewhere greater than, like, I'd say 4,000 meters. But I don't have an answer to that question.
Okay.
Other than that.
Let's see. Got a lot of questions here. Okay, next one. While in development for many years, we are yet to see a composite riser being installed. What will it take for operators to have the confidence to use it?
I think certainly the qualification, depending on how that goes. I'm sure fatigue testing is part of that qualification as well. I think the longer these pipes are in service, they'll be better understood. Particularly if you just want to look at some of the, even if it's not for dynamic application, some of the material degradation issues should become more apparent for the existing flow lines that are already in the water or jumpers that are in the water. So any issues related to that might become more apparent over the years. Hopefully there aren't any. But yeah, I think the participation of operators and collaboration with the suppliers would give them and everyone else the confidence that these are suitable for use for dynamic application.
Okay, next one, how did the different load scenarios of installation, production, and shut-in impact material selection?
Yeah, yes, certainly do need to consider a suitable polymer that can withstand the cycles of the various cycles of pressure change and temperature change. I think PVDF is the main material, and PEEK as well, that are suitable for riser applications. Although there are some other materials that can be considered, PVDF and PEEK are the main ones that can withstand the high temperatures and the pressure changes. And they've been proven within flexible risers to be suitable for such application.
Okay, great. Let's do one more question. Do you think the TCP and hybrid flexibles are replacements for flexible pipe only? And what about rigid pipe?
I think, I think primarily, particularly in deep water application, I think there would be a replacement for rigid pipe, as that's what is typically used in water depths greater than, say, 2,500 meters so far. Whereas in they can be a good replacement for flexibles, particularly if maybe if design is a concern, particularly in Brazil, where there have been recent failures due to high CO2 and environments where that's caused corrosion in the metallic layers of the flexible and it's led to failures. I think that's a good application for composite pipe to replace flexible pipe. I think it really depends on the application or the area where part of the region where these are being considered for. I think they can be replacement for both.
Okay, great. Well, I think that is all the time that we have for today, and thank you so much, Rohit, for all the information on the topic. As we discussed earlier, if we didn't get to your question or if you think of more in the meantime, you're welcome to reach out to Rohit, and you can contact him using the details provided here. Rohit, if you could go one slide back and we can show them. Rohit's email, there he is. If you want to contact him, you can shoot him a quick email directly. And also thank you all to the audience for your time and participation. We hope you found this useful and you will join us for more webinars in this series. We're still doing them every 2 weeks during this time at home. And you can check out the 2H website and LinkedIn for more details and to sign up. Please look out for a link to the recording in your email in the next 24 hours. And again, for everyone in Houston and around the Gulf Coast, please be safe with the hurricane, and we hope